this here. Okay. Is it readable from there? Okay. Let's start. Okay. Today we're gonna categorize different chaotic behaviors we discussed last week. Just as a quick recap, we found out that in even a deterministic map S, that at each time n gives you the next point. Even in this simple deterministic way, there are lots and lots of chaotic behavior that if you go along trajectories, it's hopeless to analyze, to come up with notions of regularity, to come up with notions of meaning when you're considering single trajectories. And so the chaotic behavior of single points are very hard to study. So we introduced the density approach. So we start with the density of all points, then apply the dynamics, and then look at the density, the resulting density, and then do that again and again and again, and hopefully we'll be having some kind of notion of regulation. We also talked about matrices, eigenvalues, eigenvectors, just as an approach to solve recursive equations. And also we talked about different notions of convergence, norms, and a couple of stuff about measure theory, which we won't go through because already we're going to cover 100 pages today. Okay. But don't worry, it's all a high-level understanding of different chaotic behaviors. Okay. First, we're gonna talk about Markov and Frobenius-Perron operators. So we want to study the evolution of densities under a dynamic. What is our dynamic here? For now, we're just working on deterministic maps S that at each time gives you the next step. There could be stochastic dynamics like Brownian motion, like Poisson jump processes that we will go through hopefully in the last 2 lectures. But for now, we're considering deterministic ones. And what we found out was evolution acts on densities, not only on trajectories. So this strategy of these 2 chapters, chapters 3 and 4 of the book, is to study, to come up with a formalism called Markov operators, to study the different distributions. We'll talk about Frobenius-Perron operator and then its dual or its transpose, which is Koopman operator. And in the next chapter 4, we'll talk about how these operators can give us the whole different notions. Well, okay. So if we start from a point x, if we go through, we'll have Sx as S of x afterwards, or with the density approach, we're going to have an operator that inputs the density at time 0 and outputs the density at time 1. And we saw that the first approach was individual trajectories were unstable, so it was hopeless. And now we're going to define how can we rigorously go from a distribution to the next one. So throughout the lectures, we'll be having a measurable space, X, with all the sets, sigma algebra A, measure mu, where we're talking about L1 functions over this, with bounded L1 norm. And we'll be discussing about the positive and the negative of the function. And we, of course, have this kind of decomposition. And we're going to work on L1. So when we're talking about L1, we're talking about the densities of the system we're analyzing. So what is the definition of a Markov operator? It's a linear operator from L1 to L1, so having input a density, it would output a density, with two properties. First, positivity is preserved, so if you give it a distribution, it will output, again, a positive distribution. That's the first thing. And the second thing is that it preserved the first norm on positive functions. And the intuition for this is if we have a mass, a number of particles, before and after applying the dynamics, the mass is preserved. So we're not going to kill or create new mass. Some elementary inequalities for Markov operators. So when we're talking about this, you can remember the Frobenius parent operator we talked about last week, that at each step, starting from the uniform distribution on the 0-1 interval, it was diminishing the probability of being close to 0.1/2 and then increasing the two tails. So the first one is the positive part of the Markov operator acted on a density is less than equal the operator acting on the positive part. The one that we're going to use a lot is M4, which is the contractive estimate of Markov operator. So starting from those simple formalism, we kind of get this surprising contractive estimate of the Markov operator. So after applying the dynamics, the L1 norm of the distribution is always less than equal the distribution at the start. So let's see if we can prove M3 and then M4. Okay, having in mind that we have this inequality for Markov operators, we start to integrate against to just use the definition of PF. It is nothing but integral over the norm 1 of PF. And this is from inequality M3, and we get this. And because this thing is always a probability measure, it's always positive, the absolute value of F, then we know for a fact that this is the case. So we have our terminology of contraction of the Frobenius of any Markov operator. So what we're going to use is we apply the dynamics over and over and over again and look into the behavior of the asymptotic behavior of this Markov operator over our starting density. Okay. It's also very easy to see with the same contractive property that we're going to have something like this. So after applying, so the operator P, Markov operator, is Lipschitz, and after applying n times, you can have the norm is controlled. So the two densities do not get more distant than each other. They just get closer, or they become identical. Okay. So we're going to see over and over again that applying our operator over the density would give us a single measure. And that single measure would tell us a lot about the dynamics. Okay. Just to see where the equality holds. So when we have the density before and after applying the dynamics, which we talked about as a Markov process, when the two norms are equal. So if we go into the definitions, it's just about the underlying measure mu, and the proof is exactly like the triangle inequality, and one can see that the equality holds if and only if the positive part of the measure f and the negative part have disjoint supports. If that is the case, then applying the dynamics over and over again would not give you contracting. So again, we'll see how this would be unfolded when we're talking about ergodic maps, but these are all coming from the same inequality, the contractive inequality.
Can I understand this visually as a function that crosses the x-axis only at disjoint points, not staying on this zero value for a finite interval?
The operator p?
I mean the function f, the density f. So can you explain a little bit more what they mean when you say they have disjoint supports? What will the function look like?
Yes. Yes. So for example, let me see if I can use this. Okay. So this is the distribution f. Okay, because so this is the positive part. So after applying the dynamics or after considering the Markov, because the positive part and the negative part are not overlapping, here the whole thing is just positive.
Yeah.
So this thing, actually, I think I have an example here. Yes, I have. Yeah, exactly. So consider the identity map on the 0, 1 interval. So whatever the input is, I have the same output. So it's clear that whatever f I start with, the norm are equal, yes? Now, consider the doubling map. So this is mode 1. So if I have, for example, 1/2, you can regard it as half. Then the positive and negative part of f cancel out, okay? So we have the contraction. Let me get to the ergodic behavior, and if your question is not answered, we can get back to the same thing, because I'm going to mention a lot of stuff to your answer that would be regarded in the following. Okay. Okay, and then throughout this lecture, we'll see that we're going to find the fixed points of these Markov operators. So if we apply f, consider this as the converged f star, if we apply the dynamics over f star, would be ended up with the same f star. And this is an equilibrium, and after this you can say that whatever distribution you start with, whatever trajectory you start with as your starting point, the distribution of that point x would look like f. Okay. So we talked about this, and also we're going to use Radon-Nikodym derivative to define Frobenius operator reversely. So if we have an L1 function f, and f is positive, so this is a probability distribution, the measure of a set A under f, we define it to be the function f with the underlying measure mu. So starting with a measure mu, we can define all these different measures that are absolutely continuous with respect to mu. This is the terminology used here. And it's like a derivative. That's why they call it Radon-Nikodym derivative. So f could be viewed as d mu over d mu f over d mu. Okay. So if we're talking about density f afterwards, we mean there exists a mu f, and mu f is defined with f times mu. So remember, we started with x, a sigma algebra, and a mu measure, and then starting with every density, we'll be ended up with another measure. Okay, now we're going to define the Frobenius operator. So a Frobenius operator of a density f, which we regard as Pf, is the Radon-Nikodym derivative of the counter image map. So we start with the with any set A. We look into its pre-image. We started with a density as well, and we call that one the Ferran operator of f. Okay. So the idea about the whole Ferran operator is that it's the mass, amount of probability mass, transported via the pre-image map. Okay. So we apply once the dynamics, and that would give us the operator. So if, again, this is something I'm reminding of lecture 1, the whole idea about how we look into this Markov operators is the density f assigns a number to all the interval. So consider this as an infinite dimensional vector. And the Pf is a matrix, infinite by infinite, that multiplies with this vector and outputs another vector. And this would be Pf. And then we're going to see that all behaviors of any dynamics is given by eigenvalues and eigenvectors of this operator P. Okay. Okay, now that we have defined our space X, the sigma algebra and our measure, we're going to define, for now, the deterministic dynamics we're going to talk about. Our dynamics is, of course, measurable, and it's non-singular, which means that the pre-image of any measurable measure 0 set has measure 0. So after applying dynamics, which is S, the null sets are there. You cannot create mass with your dynamics. Now, let's see if we can come up with a formula for the Frobenius operator we talked about last week. So let's say I start with a density, a probability. I use the definition I had, and now I want to see if this thing exists. So from any set A, I want to define a density Pf. And what is that density? It is exactly the pre-image of the starting density. Okay. Because the Radon-Nikodym derivative is unique, so is the Pf, and hence the formula that we had is correct. Okay. So this is the first kind of operator that we talked about last week. But this is the measure theoretic formalism for defining the operator. So if I start with, for example, instead of a set A, here any Borel set could be in our sigma algebra. If I start with 0 to x, and then take the derivative with respect to x of both sides, I would be given a closed form formula for pfx. It would be d over dx of whatever is in the right hand side. Okay? Which is exactly this. The Radon-Nikodym derivative of starting measure and the pre-image with respect to the starting measure. Okay, here I applied the same a to x interval, and by using the identity I have, I give the formula for Frobenius operator. So, one other thing I want to mention here is if I change the variables, which I can if the dynamics is invertible, which is not the case most of the times, you can have integral over the inverse of S and the Jacobian matrix here. So an intuition behind parent operator is it acts, it goes and sum all the pre-image mass that you had with a different mass. And what is that difference in weighting? Is the inverse of your Jacobian. The Jacobian given by your pre-image map. Okay? Okay. Let's see examples. So, let's say my dynamics is S of x is e to the power of x. So let's see explicitly the parent operator. I see the inverse of S is logarithm of x, and looking back to the formula, which was this, I take derivative, I get to the parent operator is 1 over x, f of the logarithm of x. So if I start with a uniform distribution, I would end up in 1 over 2x of another interval. So if I start with the left distribution, I would end up with this kind of distribution. There are two key points. The support of the two measures are not the same. Okay, that's one key. So during our analysis, we should take care of this change of the support. That one thing. And another thing is, as you can see, it looks like the parent operator for this measure and the same dynamics is acting exponential, which is kind of expected. Why? Because the dynamics itself is exponential. Okay. So this alternative viewpoint that you can view dynamics as your Markov operators is coming from this intuition, which is the very definition of our Markov operators. This is also some measure theoretic, which is we don't go into very often. All arguments we're going to talk about is almost every x. And what that means is we don't care about measure 0 points. If you remember from lecture 1, even in very simplistic dynamics, there are some non-chaotic points, like some points that would behave periodic, some points that are constant, but we don't care about them because the measure of all those non-chaotic points is 0. And we'll be talking about the support of f, and what we mean is exactly with respect to non-zero measurable sets. Okay, this is for two-dimensional parent operators. I just put it there to see that, okay, the whole formula is not some crazy stuff. It's just coming from first principles. So if you have, again, some dynamics in two-dimensional, which is invertible, and by change of variables, you can have the same formula for your Markov operator. Okay, I won't go through this proof because I don't have enough time. Now we're going to talk about the dual of Frobenius operator. So the Frobenius operator acts on densities, on L1 functions. So we can ask what is the dual. What is the dual operator respecting to the parent operator? What is the dual of L1? Is
L infinity.
L infinity. So we need to, in order to define the other dual operator, the dual operator would act on L infinity, on measures instead of the densities. This is some technicalities about the duality of L1 and L infinity, because the dual L infinity is not L1. And Koopman operator is nothing but the dual of parent operator. So remember all the formula we had for parent operator? The Koopman operator is just given by UF of x. It's nothing but f after applying the dynamics once. You can already see why the parent and Koopman operators are the dual of each other. So if you write down the integral formula, let's see if I can do it here. So if I have PF and G, okay, which is defined as integral over the whole space x, PF of x, Gx. This is nothing but, if I consider the dual of P, which is U, this would be, if I write down the definition of PF, it would be Fx Ug x, whole space. So when I say, this is kind of cool, because I wrote in mirror, not, because I couldn't. Okay. So, yes. So when I say the dual of P is G, the dual of parent operator is Koopman operator, what I mean is this. So I can have this identity. So that's why I say it's like a transpose. It's like a dual. Okay. Okay, and so whatever argument we're going to say about the Farren operator, the dual argument would go for the Koopman operator. From L1, we'll go about L infinity. Okay. I think the first part was exhaustive, so before going into details, let me...
Sorry, what does U act on? U acts on densities?
U acts on the measures, L infinity. So, so here, let me look into this identity. So for example, G, which would be something that you would act on, is one, whether you are in a measurable set A, and zero otherwise, okay? Let's compute PF dot 1A. This is the integral of PFX mu dx over just A, right? Okay. Now, what is the definition of U1 of A? Again, U acts on L infinity. This is L infinity, right? Okay, this is the definition of Koopman operators. Okay? 1A of Sx is U of 1 of x, right? Here we have the same. U of f of something is f of s of something, right? Okay? Now we want to see if these two are equal. So if I do a change of variables, I can have, if Sx is in A, it's the same as if x is in the pre-image of A, right? So these two quantities are indeed the same. And because we started with a simple function, remember the whole definition of simple function, which was constant on a set, on a measurable set, okay? So because we proved the duality of Koopman and Farron operator on a simple function, so we can say that they are each other's dual on the whole space, right? Simple functions are dense in L infinity, okay? Okay. Before showing this technique, let me go through this example. That. Okay. Okay. So, until now, we looked into a simple example last week. We also talked about Markov operators. And now we want to see, can we identify different chaotic behaviors? Okay. So first, let's see what are some possible chaotic behaviors. So the most famous one is ergodic behavior. Okay. So in all these examples, I start with the same cube, okay? I apply different dynamics, which we'll see all of them are measure preserving, okay? But all of them are ergodic. Okay. Let's see, for example, what is ergodic here. Let's say I want to sample from I want to get a random number, okay, from 0, 1 interval. What is the procedure? Let's say I want to get a sample, a uniform sample, from 0 to 1.
Pick a random bit, pick a random bit, pick a random bit.
0, 1. That's cool, yes. But what if I want to start with a random C, as in different experiments, and then apply my algorithm and report my numbers? I want to give you the same C that when you start with, you end up with the same experiment. So I want you to give me a deterministic kind of random numbers fitting. What can I do? Let's say I start from seed 42, that everyone starts with, for whatever reason. What is the logic here? How can we start from some deterministic number, but we end up with a random number generated from 0 to 1 interval?
If you apply some mixing process to it, like von Neumann proposed squaring the number and taking the middle bits. I think modern algorithms like use some bit swapping and all sorts of crazy things.
So regardless, I start with from 42 or 52 or whatever seed I start with, if I apply this kind of dynamics that you very interestingly described as mixing, I end up with a uniform distribution from 0 to 1, right?
Is that why they call it mixing? That's kind of cool.
That's not the terminology, but what you just described is an ergodic behavior. So if I look into, for example, what does it mean to generate a random number from 0 to 1? If I take the interval 1/2 to 1, and I apply this dynamics that, let's say it's purely random, the number of times I would end up in the upper interval would be 1/2, right? That's the whole notion that we want from a random generating process. Though the dynamics itself is kind of chaotic, right? So that's the notion of ergodicity. We'll see rigorously what does ergodicity mean, but look at here. So I start from x and y, and after applying the dynamics, I would go to x plus some irrational number, y and some irrational number, okay? Though, because of this irrationality, the probability of hitting any small interval here is uniform, right? Because this dynamic, though it's deterministic, if you give it enough time, it can generate all random events that you want uniformly. And the reason is, again, all bits in this irrational number are generated there.
I wouldn't want to, secure my bank account with that, surely.
Like if you look at the points with x plus square root of 2 times n, an integer, then those points would get higher probability than others. They are the only points that touch. I said, like, if you don't look at rational numbers, but if you, like, say, because you said if you look at any points, the density would be uniform, but what if I'm extra picky and just, like, pick the irrational points, then...
Because it's uniform in n, right?
Yes, so
just keep taking more n.
let's say I'm on this point, okay? After applying each time the dynamics, I'm going to move my vector theta, okay?
Okay.
Let's say theta equals, okay, now I need
You're
to,
taking a mod after adding
yes,
those
yeah,
numbers, so, okay.
that's the whole point, yes.
Yeah.
It's like gluing this to this side to this side and gluing this side to this side. And then if you look at irrational points, it would go over all points uniformly if you look long enough into time. Okay.
Okay.
Another behavior that is still ergodic, okay, is this map. X plus y, starting from x and y, x plus y, and x plus 2y. Okay? So I start with this small cube as I started here, but after each time I apply the dynamics, you can see that starts to mix into the space. This is also chaotic. So if I look into each point's orbits through time, it's the uniform distribution over the rectangle at the end of the day. But the behavior is kind of much more interesting, much different than this. Though the notion of uniform probability is still here. But if you add up the small rectangles that are affected by this dynamics, still the measure of all of them is the same as this cube. Okay? But in the right hand side, which we'll be regarding as the exact chaotic behavior, would spread out into the whole space uniformly, no matter how small this is. This is the notion of exactness. Okay. Now, there are a couple of interesting arguments said in the book. So let's say I observe a dynamical system. Okay, I look into the trajectory of a single point, the orbit. Most of the time, I can say whether it's ergodic or no. How? With this uniform distribution. If the orbit looks uniform at the end of each single point, then I can say it's ergodic. But it's good to pause and ponder about how can I state that something is mixing? How can I prove that some process, some dynamical process, is mixing? Or exact with this informal definition that whatever small measure I start with, after applying the dynamics, I'm going to be all over the place. Okay. So I go into my experiment, I observe some movement of particles of something, and a note. Here the dynamics is deterministic, and we're observing all this crazy behavior. What could happen with Brownian motion? With stochastic dynamics. Okay. All these notions of Markov operators that we went through are going to be essential when we're talking about ergodic behavior. So we'll see them emerge to prove different things are ergodic, mixing, or exact. Okay. So this is chapter 4, studying chaos with densities. So we are going to see the long-term behavior of a density when we're applying Frobenius operator or its dual Koopman operator. We are going to work with some interesting transformations. So the dynamics is not arbitrary. At least is measure preserving, or MPM, measure preserving maps. And the definition is the pre-image of any set, the measure of that set, is the same as the measure of the set itself. Question. Is this the same as mu of A equals mu of SA? So does MPM means mu of SA equals mu of A? Yes.
S is not necessarily a bijection, right?
Yes, it's not.
So in general, S inverse S is not necessarily
Yes.
the identity.
So that's the key point. So when you're thinking of measure preserving map, though the very definition looks like it preserved the mass after applying the map, it's kind of the reverse. It preserved the mass on the pre-image, not the image itself. So to see the difference is, here. So consider this map, Aradic transformation. Let's for simplicity say that S of x is 2x mod 1. So I start with any interval, I make it double. Is this measure preserving? Let's say I start with the interval 0 to 1/2. I end up with 0 to 1. Is this measure preserving?
No.
Your guess is, it is indeed measure preserving. Let's see. So again, measure preserving does not think of forward dynamics. It's all about backward dynamics. So the measure of an interval 0 to 0.1, after applying the dynamics over and over again, it gets to 1. 0 to 1, yes? But it is measure preserving. Why? Because this map is not invertible. Let's calculate the pre-image of the interval 0 to b. Okay? The mass of this interval is b. What is the pre-image of b? I start either from 0 to b half, or 1/2 until 1/2 plus b half. Okay? What is the measure of this? B. What is the measure I end up with? B. So it is indeed a measure preserving. So I want to kill this wrong intuition that measure preserving is forward. No, measure preserving is talking about backward. And that's the whole notion that we differentiate exactness from mixing behavior. Okay.
Do you have a little intuition of why it's defined with backward, not forward? If you have it later, it's fine.
So the backward is more interesting because you can define parent operator. And the parent operator was about pre-image. If you want to look into the forward direction and define something like that, you need to define it on the dual of density, which is L infinity. So,
you mean the identity which is integrating PF is equal to integrating F over
the pre-image, yes. So put F equals identical on the whole space for that, for the definition of parent operator, okay? Then you'll need something like measure preserving map.
Okay.
And already you see that lots of maps, if I define measure preserving as a forward thing, lots of maps that are interesting like this are not going to be measure preserving. We'll be talking about just invertible maps. That's another reason that we define it like this. Okay.
So I have a guess for like physically why it is so. Maybe because you want to like look at the final product of some dynamical system, like in its steady state. So when you say it's mixing, or when you say it's ergodic or exact, you mean the end product of that dynamical state is like you want to study properties of that thing, not the initial condition. So you want to go backward. Is that reasonable?
Yes. I mean, I don't know physics, but it looks, yeah, it looks logical, yes.
Okay.
Yes. Okay. Now, one question is, a measure is invariant. So when we say a measure is invariant, it means that the dynamics applied on the measure is measure preserving. Okay. When I say a measure is invariant under some dynamics, it means that the dynamics is measure preserving with respect to the measure. Okay. So here the cool theorem. I mean, the proof is very simple. It's just the definition of measure preserving map and the operator, the parent operator. It says that a measure is invariant if and only if the density F is a fixed point of parent operator. Okay. This is also the whole definition of a measure preserving. This identity would give rise to the proof. So it's nothing but changing the definitions from parent operator to measure preserving dynamical system. Okay. Okay. And in all these examples of random number generating we worked with, what was the invariant measure? It was the uniform distribution over 0 to 1, right? That after we apply this random process of generating random numbers, if I start with the uniform distribution over 0, 1 interval, that would end up into the 0, 1 uniform distribution. So the invariant measure, or the fixed point f, in all of those cases was what? Was the uniform distribution, right? Okay. We'll see that this whole thing would enable us to define ergodicity.
Sorry, I have a question on the last slide. So when you said measure preserving is equal to being a fixed point, I'm imagining a 1D function. So like if for a fixed point, then p is mapping the function back to itself. But it sounds to me like measure preserving is you just need to measure, like for example, the example you gave, like 2x mod 1, it maps different intervals together. Mm-hmm. So it does not preserve the density function. Like the density function would change, but its measure doesn't change.
So, for example, in the same example, let's say I have 2, okay? If I start with a strip, I go around the circle once, okay? What is, if I apply the dynamics again, each point is stretched, yes?
Yes.
Okay. How many I have after applying the dynamics? This is what I would end up with, yes?
Yes.
Right?
Yes.
Okay. Now, Q's. So this is a uniform distribution over the whole circle?
Yes, yes.
Now, what I end up with is also uniform, right? This is 2, 2, 2, 2. Instead of going around the circle once, each point of the circle is traveled twice. So still I have uniform distribution.
Yes.
So if I normalize, I would end up with a uniform distribution still.
Yes. Okay.
So measure preserving, this map was measure preserving,
okay.
and the fixed point
I see.
of the density was uniform as well.
Okay.
So again, what this says is that some dynamics is measure preserving if and only if the underlying measure is the fixed point of the parent operator.
Yes, okay. Yes. Okay, thank you.
Okay, so this is the paradox of, this is like the mistake by the whole measure preserving notion. So measure is preserved under the pullback S minus 1, not forward images S and A. This is the example that we talked about in the first session. So for those of who were not here, this was the function. So if I start from here, I would end up here, then I would go here, then I would go here. So this was the dynamics S. Sorry, I need to write like this. This is the dynamic S, and the end up measure, the constant, the converging measure that we ended up with was this. The reason is kind of obvious, because if I start from 1/2, I would end up on 1/2. So the measure of 1/2 is 0. doesn't matter. But if I start with an interval here, I would be repelled from 1/2 and would go to close to 1. So for that measure, if for that density, we calculated the parent operator, and it was this. And it can be proven that the solution to this formula is nothing but what we just described here. Quick question, what does it mean? This equation, what does it mean? What is F for P? It's eigenvector, yes. So we define for a measure preserving map, we define a parent operator, and it kind of automatically pushes us to define the eigenvectors or generalized eigenvectors. There is this other Baker transformation, which is interesting. So at each point x and y, I would stretch in x and contract in y if I'm in the first interval. And I just do the same with some correction if I'm in the upper interval. So it's a stretching here and contracting there, like this. I start with this whole rectangle, I stretch, and then put these on top of each other. Okay. This is the Baker transformation. And the name is because when you want to
dough.
you want to make a bread, you stretch and then put on top. So the counter image of a set. So if I want to calculate the counter image of a set A, I need to do the opposite. Of course, this is the counter image, and the counter image of something upper half, which makes the whole thing measure preserving, is exactly this. Okay, so again, because of non-invertibility, forward map and backward map are very much different. Okay. Okay, and one can see that in this example, the measure preserving, the convergent distribution is uniform. Okay, so if you want to cook a bread, applying this dynamics is the best thing that you can do, because everything is mixed with the same probability, uniform probability. Okay. Some very interesting one that will, I hope we can prove that this is not only ergodic but also mixing, is this onus of diffeomorphism. So starting from x and y, I add up the first and I add up the second with twice the y. Okay. And already one can see, so if I apply the dynamics again, what do I have? 2x plus 3y. Here I would have 2x plus how many y? 5. So you can see already Fibonacci sequence. Okay. And if you remember from last week, one of the Fibonacci sequence, this is Fibonacci, the eigenvalues of this are very much like the eigenvalues of Fibonacci sequence, but just inverse. So you can see that it stretches in this direction and contracts in the other direction, which correspond to the eigenvalues. One of them is stretched and one of them is contracted. Okay. And again, if I start with the rectangle up left, what I would end up with is this. And of course, we're working in mod 1, so I need to glue everything back to each other, and I would end up with this. So starting from here, I would end up like this. And you can already see this is a chaotic behavior, but it looks like the uniform distribution is kept uniform under this transformation. Okay. So we kind of want this to be ergodic. Okay, let's talk about ergodic transformation. Okay, until now we talked about measure preserving maps, and also it meant stationary density. But let's see, for example, the identity dynamics. Whatever I input, I output the same. Okay, this is measure preserving, of course, not only in forward but also in backward. So, is this interesting? So, if I start from a point x0, and if I look into the orbit of x0, I would be at the point x0 again and again and again. So it does not have some mixing property, right? So I want to discard this kind of dynamics, though they are measure preserving. Okay. The notion of ergodicity exactly is this. Some dynamics S with respect to our space X and measure and the sigma algebra is ergodic if and only if the only two invariant subsets are either the zero set or the whole set. And what is an invariant subset? Is all those sets that the pre-image is preserved. Okay. Remember, the measure of these two are equal, but if they are equal themselves, this means those sets are invariant. Okay. And we say some dynamical system is ergodic if the invariant subsets are just the zero subset and the whole space. Of course, if I apply the dynamics to the whole space, I would end up to the whole space. But there is no other decomposition of the space into two invariant subsets. And that's what I mean by ergodicity. Okay. Okay. This theorem connects what we describe as ergodic and being a constant density function. So if we are in a measurable space and we have this non-singular transformation, then S, our dynamics, is ergodic if and only if for every measurable function f of Sx equals Fx. Then this would imply that f is constant, or f is the uniform distribution. Okay? So this is the whole connection between ergodicity and uniform distribution. So if I want to create some random generating process, random number generating process, which wants to be uniform, all I need to do is to come up with a dynamics S that is ergodic. Okay, let's see the proof. So let's say f is not constant, it's not uniform. Then there exists a number r that the two sets below r and above r have positive measure. Okay, this is because f is not constant. Okay, look into the pre-image. S minus a is exactly this. And remember, f of S of x was fx. So the pre-image of a is a, and the pre-image of b is b. So a and b are invariant sets. But they had positive measures as well, so this contradicts with ergodicity. This is one way proof. Another one is assume S is not ergodic, then there exists a set a non-zero set, a non-trivial set, that the pre-image is the same as the set itself. Define the function to be 1 in that measurable set and 0 otherwise. Then if you define, if you look into the definition of f, you see that f of s of x equals 1ax. But f is not constant. It's 1 and 0. So you can see the trick of defining ergodicity, which means invariant sets are trivial with the uniform distribution. Okay, so this is the relationship between ergodicity and uniform distribution. And of course, it has a dual concept with the Koopman operator. I just need to go from P to U. P as my parent operator and U as my Koopman operator. So Koopman operator was FOS, and we had the FOS equals F. So exactly the function would have this property. So the same theorem here as here for the Koopman operator would be some dynamical system is ergodic if and only if the fixed points of Koopman operator is constants. Okay? And as you can see, this is very close again to invariant sets. Okay, let me go for an example. We can get back to the proofs if we had time. So, to see an example of ergodic dynamical system, look into the circle I just went through, and let's say, starting from the point x, I end up with x plus phi, an offset. If the offset with respect to 2 pi is, let's say 1, okay, or some other rational number, then if I look into the orbits of each point, they're going to be repeated after some time, okay? So those orbits are invariant sets. But we said if something is going to be ergodic, the invariant sets should be trivial. So this thing is not ergodic. Okay.
What are the invariant sets exactly?
The invariant sets are sets that the pre-image of the set is the set itself. For example, let's say I add pi over 3.
Oh, so it's like the 3 points on the triangle.
The 3 points would be invariant sets, would be an invariant subset. The pre-image of those 3 would be those 3 itself. And also those the measure of them is non-trivial, could be, let's say, 1/3. You just coarse the intervals, and then it does not have measure 0, not measure 1, it has some non-trivial measure. So we found some invariant subsets that is not empty, so the whole system is not ergodic.
The 3 points on their own would be measure 0, so they would be fine.
Yeah.
But if you fill them in...
Yeah, with an epsilon.
Okay.
Yes. Exactly like this. So if I go with a period, this is an invariant set, but it has measure not 0, not 1, so the whole thing is not ergodic. And this is the very interesting thing about ergodic theorem, Markov ergodic theorem. So ergodicity and uniform distribution would enable us to disregard the whole sampling process. Let me show you this. So let's say I want to sample when I say sample, let's say I have a population, and I want to sample from that population, okay? The ergodicity, if S is ergodic, with Birkhoff ergodic theorem, we can prove that if you want to measure the integral right-hand side, which you go over the whole space in once and calculate the measure of that set, okay? What you can do is to look at the orbit of single point. So I need to look into the orbit of one single point for long enough time, and that would be equal to the whole space measure. Okay. I remember, so a dynamical system is ergodic if the orbit of each starting point would converge to the same distribution, regardless of the point x I started with. The whole thing is about being regardless of x. So it doesn't matter if I start from, let's say, 12 o'clock in my ergodic theorem, and I look into the orbit, I would traverse all the circle. And if I start from clock 3 and do the dynamics over and over again, I would end up to the same uniform distribution. Okay? And also this enables us, let's say I want to generate a random number from interval 1/3 to 2/3. Okay? With uniform distribution. What I can do is apply the Birkhoff ergodic theorem. I start with whatever number I have in 0, 1, and I apply my ergodic dynamical system. Whenever I hit the interval, I increase the hit number, and whenever I don't hit, I add to the denominator. And that number would give me the probability of hitting that interval, because the whole thing is ergodic. Okay. Is ergodicity clear? Any questions? Okay. Okay, we have two more chaotic behaviors. One is mixing and one is exactness. So again, we're working with a measure preserving map, an NPM, which satisfies this. And we talked about ergodicity. Okay. Now what is the definition of mixing? Okay. A measure preserving map S is mixing if I start at A and the pre-image nth time pre-image of B, I end up with the probability of A and B for any A and B. Okay? I can give you an example. Okay. Look. So I start from a set A and a set B. Okay? What are the pre-images of B in the Baker transformation? So we split and then put on top. We split and then put on top. So what is the pre-image of B is this, right? What is the pre-image of this is these two. What is the pre-image of this is these four. Okay? And if I do this again and again and again, I would end up with small horizontal lines. Okay? And what is the quantity here? The left-hand side. Everything, sorry. Okay. What is the quantity left-hand side? Is the intersection of those pre-images, right? The pre-images. So it's these two, is this, okay? And now look, what was the measure A times measure B? Measure B is 1/2 of the whole rectangle, right? So measure A times measure B would be half of measure A. And look, if I do this again and again and again, the intersection is exactly half. Okay. And because the whole thing is ergodic, you can look into the forward images as well. So this is some notion of chaotic behavior that we categorize. I want to prove to you that anything that is mixing is already ergodic. Okay? Let's see. Let's start with an invariant set B. And let's say it's invariant, okay? I can apply this identity again and again and again, and I would end up in S nth pre-image of B equals B. Okay. Define A to be X minus B. Then the measure of this set, because S minus nth pre-image is exactly B, and this is the definition, this is 0, right? By mixing, we had that this intersection, the limit, which is always 0, so the limit is 0, equals mu A times mu B. So mu A times mu B equals 0, and because of the probability measure mu, the probability of some set X minus B is exactly 1 minus measure of B. So you see that we started with any invariant set, and the measure should be either 1 or 0. So any mixing behavior is already chaotic, is already ergodic. So the Anosov transformation, the Aradic transformation are some examples of mixing, but the rotation transformation is not mixing. Is that clear for you? That why the rotation is not mixing? Let's say again with the 1/3 and any other set. So if I look into the pre-image of 1/3, stays the same, so it's not mixing. Okay. Okay. Some other example is the example we had for dyadic transformation. If I start from a 0 to B interval, the S minus B becomes a very small disjoint of B over n intervals, B over 2 to the power of n intervals, small intervals. So we already expect that this thing, so the pre-image, n pre-image of B is measure B, but with very fine approximations. So if I want to approximate the measure of A with those small stuff, it's the same as this. Okay. So I have more and more, when I calculate the pre-image of any set B, I would have more and more to the power of n more small intervals. So I can approximate the measure A with these pre-images. And that's the reason the whole thing is mixed. Okay. And the last category is exactness. And this is where the whole difference from measure preserving that looks into pre-image rather than forward image is different. So if I start with the same x, a, and mu, and I have a measure preserving map, S is exact if whatever subset I start with that has non-zero measure, if I look into the forward images of A, the measure of those sets would be 1. So it would explode. Again, the S is measure preserving. Okay. So for example, in our 2 times x, if I start with whatever small interval, at each time I'm making the set bigger and bigger and bigger. And because everything is normalized, the measure I end up with is 1. Remember, if we don't normalize, it could be the case that the measure is greater than 1, right? Because the map is not bijection.
Just like mu x, right?
What?
You just purchase mu x then.
Not mu x neither, because, for example, if I have the circle and put measure 2 on each interval, okay? Then apply the dynamics on the whole space once, okay? What's the measure of the whole circle? It would be 4.
But each little patch gets stretched out by a factor of 2, right?
Yes. So the measure of this, the whole space with respect to the starting measure would be to the power of 2, to the power of 2. After another applying, I end up with 2, 4, 8. So that's the reason I want to start with something normalized, so I don't normalize each time.
So like 1 to the n.
Yes, exactly. Okay. You can prove that whatever that is exact, whatever process that is exact, is already mixing, and whatever was mixing was, of course, ergodic. Okay. But of course, the inverse is not true. So this is a fact that we already expect. If our dynamics S is invertible, then of course you cannot be exact. Why? Just change A with S minus A, because this is invertible. Then you will end up with this. Then you will, whatever forward dynamics you apply, you have the same measure. So you cannot be exact. Okay. So we have these 3 different notions of chaotic behavior. One is ergodic, which you can see over and over in many different applications, mixing, and exactness. Okay. This is the image we talked about. Okay. So you can see that ergodicity is shared among all these 3 dynamics. And look into the uniform distribution. So whenever you want to think of ergodicity, take any interval, the number of times you hit into that interval should be uniform. If that is the case, then you're ergodic. For mixing, you can see that you get finer and finer. That's the intuition for mixing. So if you look at the end pre-image, it's like all over spread out the space, so you can approximate. That's the intuition for mixing. And for exactness, whatever measure you start with, you'll be going to the whole space. Okay. Now in the last 3 minutes, I just want to go over how we can prove something is mixing, something is ergodic. But if we want to go through the proofs, we'll be doing that next week. But this is very interesting to just see the result. Remember, last week we talked about 3 different notions of convergence. One was Cesaro convergence, one was weak convergence, and one was strong convergence. Okay? Now, a measure preserving map S is ergodic if and only if, what was the weakest notion of convergence? If P and F is Cesaro convergent to 1 for all F I start with. It is mixing if and only if P and F is weakly convergent to 1. Okay, when something is Cesaro convergent to 1, it is of course weakly convergent to 1 as well. Right? Right?
Yeah. Wait, no, we have that backwards.
Yes.
Strong
exactly.
implies weak implies Cesaro.
Exactly. So when I have something mixing, I am weakly convergent to 1. I am Cesaro convergent to 1. So I'm ergodic. Okay. And of course, if the dynamics is exact, then it is the case that P and F is strongly convergent to 1. Okay? So how I get to the uniform distribution is governed by the chaotic behavior. The takeaway here is, let's say I want to randomly generate a uniform distribution from 0 to 1. Which of these 3 is better? All of them at the end of the day would give me a uniform distribution from 0 to 1 if I look into the orbit. But which one is faster?
Strong.
So strong is a better notion. Because if I can create a strong dynamic, an exact dynamic, I would be already mixing and ergodic, but I would have faster convergence, right? So the different notions of chaotic behavior corresponds to different notions of convergence.
That's really nice.
Of course, you can, all of these are about parent operator. We can talk about the dual operator, Koopman, and have the same thing. So this is again the different notions of convergence. If you don't remember what was Cesaro convergence. So the 1 over n of some sequence is converging. Weakly convergence is for all G, for all test functions. The P and F corresponds to 1. And exactness is in a strong topology. The 2 are the same. Okay? And again, the thing that we want to converge to is 1, is the uniform distribution. So all of them has this notion of uniform distribution at the end. So the orbits would traverse the whole space with the same uniform measure. Okay. Think we're out of time, but I would upload the slides, and of course you can access to the book as well. It's very interesting to prove. For example, this map is mixing. So what should I do to prove this is mixing? Apply reconvergence. Okay, let's...
Do we know what the parent operator is for that map?
Yes, we know. We calculated it in the first half of the lecture. I have the exact formula, yes. So look, in order to prove this map, which remember, this was like very much like Fibonacci sequence. If you look into S2, it would be Fibonacci sequences of y and x, the coefficient. And in order to prove the weak convergence, you need to come up with a dense basis of the dual space, which you can take sine and cosine, okay? And then you need to prove weak convergence. Just hand waving, this is the coefficients of S and X, this is Fibonacci sequence, okay? And then I want to calculate the UN of GXY, okay? This would be the result, okay? Okay, so this is the basis, KL, sorry, I need to do this, KL, okay? And these are the Fibonacci sequence. And remember, the base is integers. So K and L are integers, right? So I go ahead and calculate the inner product of f, of any f, the f I started with any test function u and g. And what I end up with is this. And remember, sine and cosine are perpendicular to each other. And the only way I can get a 1 is that these things are equal, or they equal 0, okay? I write down the condition for this. I have the formula for this. And very surprisingly, what I end up with is K times this plus L minus P over this equals 0, okay? And the whole magic of the proof is here. This is a natural number. This is a natural number. This is the 2n minus 1 Fibonacci number. This is a natural number. This is a natural number. But what is this? As n goes to infinity. This is the eigenvalue, the inverse of the eigenvalue of Fibonacci sequence, right? The ratio between these two. Okay? So, in order for those two to create 1, you need this thing to be 0. A natural number 2 times a natural number over an irrational number, 0. Is that possible? No.
That's a pretty clean proof.
Yes. So, therefore, it indeed converges weakly to 1. Of course, this was hand waving, but the core idea behind the proof is the Fibonacci sequence, though it creates natural number, the asymptotic behavior is governed by some irrational number. Okay? So the whole thing is mixing. Yes.
And you used this, very specific choice of basis from some kind of density argument.
Yes, I can choose this as my base. Why? Because this is dense. Sine and cosine is dense in L infinity. I think in L1, let's say, because LP, yes. Okay, we need to wrap up. There are other notions of chaotic behavior, which I ask you to go and read about Kolmogorov automorphisms in the book, but we don't be using this forward. But these, of course, you can have other terms of convergence, the sequences. So you can give different notions of chaotic behavior, which is weak mixing, and with K automorphisms. So you can look into that as well. Yes. So to conclude, we talked about, again, a deterministic dynamical system. We looked into trajectories, we saw chaotic behavior. We said, okay, what are some chaotic behaviors that I can categorize? And we came up with convergence to the uniform distribution of trajectories. And the convergence can happen in different 3 stages: weak convergence, strong convergence, or Cesaro convergence. And that was our machinery to define different categories of chaotic behavior. Next time, either we'll go through the proofs, I will see the feedback, or we start to talk about continuous time dynamics. So instead of talking about p to the power of n of some density, we'll try to define what was the name? So I have the Persian name in my mind, but I don't remember the English name. So instead of Pn, I need to come up with a continuous form in t, in time t, continuous time t, of the same parent operator, of the same Koopman operator, of the same dynamic S, and then I can hopefully talk about chaotic behaviors of continuous time dynamics. Okay? Questions? Or anything? Let me end the lecture with this. Yes. Mm-hmm.
Like the mental picture with continuous time is still the same, right? You still follow the trajectory continuous time, but you're not applying a sequence of maps.
Yes.
You're doing something a bit different.
Yes, and what is the x? So we have p squared, p to the power of 3, p to the power of 4, p to the, etc. And
like a matrix.
the whole thing is linear. So again, if you remember from the first section, we wanted to solve a recursive map, a recursive equation. An equals 2. Sorry, my mirror handwriting is not that good. Okay. This would end up with 2 to the power of n, a0, right? Now, what is the continuous analog of this?
Like this with the derivative.
A t derivative with respect to t equals ct at. What is the solution? Let's say this is
E to the integral of ct.
Yeah. Or e to the power of integral of ct dt a0, right? And if you want to, so if I start with this equation, which is linear, so call this P F. Okay. How can I get P, which is this C here? Sorry, this is P, this is F, this is PF. Okay. If I have the solution, what is the definition of P here? It would be the derivative of this, and then derivative of this, and take the time small and small and small. Infinitesimal generator. Yes, that was the English term for the continuous version of Markov operator. Instead of discrete time, it would be infinitesimal generator of a random process, or a dynamical system, continuous system. Yes, I hope this was interesting. Next week, hopefully, in the first half, I would talk about some simulations to motivate people back that may be scared of this different mathematics groups. Okay. Thanks. And this.